Hello everyone. If you're joining us after watching part 1, then welcome back. If you haven't watched part 1 of the video on z-score and standardization, you might want to watch that first. What we're going to be doing in this video is we're talking about another use of the z-distribution, namely using it to compare scores from different normal distributions. To do this, I'm going to present an example. Let's say that I've taken an exam, one in verbal, one in numerical. Okay, and say that the verbal scores, let's denote it by V, for the whole year, turns out to be normally distributed with a mean of 50 and a standard deviation of 5, so variance of 5 squared. The numerical exam, let's not use n because n is used for normal, so let's say this is the thing about notation, let n u be numerical, normal distribution, mean of 50 and standard deviation of 12. Okay, so let's have a think what this looks like if we were to sketch this. These are the scores on the x-axis. For the verbal, like this, tapering off either side towards 0, and it's centered around 50. Alright, so let's just say, so along this axis would be for this one V. Let's just do that one. Right, how about for the numerical? Right, it's normal, so it's also a bell-shaped curve. It's centered on 50 now, so it's centered along here as well, isn't it? Okay, so is it going to be the exact same curve? No, it's not, because can you see that the standard deviation is bigger than for verbal? What does this mean? It means it's more spread out, isn't it? Now, because the area in the curve adds to 1, you can imagine that if I squash this peak downwards, because I've got to get it flatter, if I squash this peak downwards, then these bits here, the tails, what we call the tails, will fatten out. So then I'll end up with more or less something like, oops, it's supposed to go towards 0. Something you can imagine smoother, going towards 0. Something like that. If this was an art class, no doubt I'd have failed the course. Okay. So in red is the numerical distribution, normal distribution for the numerical scores. Now say I scored for the verbal 55 and the numerical I scored 60, then if we look at, compare it to the mean for the verbal is 50, I've scored 55, so I've scored above average. Numerical, the mean for the numerical for the whole year group was 50 as well, and I've scored 60, so again I've scored above average. And comparing these two, it looks like I have done better. It's not that looks like I have done better in the numerical than the verbal. But how did I do relative to everyone else? We can answer that by computing the z-score for each of my scores here. So for the verbal, which I got 55, the z-score for that, recall that what we do is we take the score, in this case it's V, subtract the mean, and the mean is 50, divide by the standard deviation, and that is 5. Okay, I'm using this result here for the verbal. So 55 substitute into here, 55 minus 50 over 5, and that gives me 1. Similarly, for the numerical, the z-score for the numerical, I got 60. Subtract the mean for the numerical, 50 over the standard deviation, which was 12 for the numerical. These are where I got the numbers from. So numerical, the mean, the standard deviation 12, and the variance 12 squared. And that comes to 0.83. Okay. Now, how to interpret the z-score, because the z-score tells me how I have done relative to everyone else in the class. Well, look, for the verbal, the z-score is 1. The z-score for the numerical is lower, 0.83. It's lower, that's the main thing. What that tells me is that relative to everybody else in the year group, I've done better at verbal than numerical. Why? Let's look at it in terms of a picture. 0. Z-score of 1. Okay, if we look at the tables, we find that the area comes to about 0.16. Let's express that in terms of percent. 16%. That's obtained from the standard normal tables. For the numerical, the z-score was 0.83 for numerical. Z, 0, 0.83, 0.83. Clearly, the area must be larger than for the z-score of 1. It comes to 20%. So everybody in year group, all the scores in year group used to get this histogram. And how we can interpret this as z-score of 1 is to say that only 16% of the other people have done better than me, and obviously the opposite, 1 minus 16%, 84% didn't do as well as me. If we go to the numerical test, we can see 20% scored more than I did. So from this, you can see that I have done, relative to everybody else in the class, I've done better at verbal than numerical, and that is the case, and this is the thing, that is the case even though it would appear from the initial data that I have done better at numerical. Why? Because remember the untransformed scores for the verbal, I said 55, and for the numerical I had scored 60 here. So if without standardization, 60 is bigger than 55, you'd think, well, I have done better at numerical, that's for sure. But if we compare it to other people in the class, that 60, although it's high, other people in the class, obviously a lot of them also scored high as well. Whereas this one, I've scored 55, which is lower, but actually it might be a harder test, but fewer people scored higher than I did. Okay, so that's you wouldn't be able to see that without computing the z-score. So again, in this case, we've looked at the use of the z-score where we are comparing the scores between more than 2 or more normal distributions. In this case, we're looking at comparing 2 normal distributions, 1 for the verbal, 1 for the numerical. Okay, to see if to help you with the understanding, let's just finish off with an exercise. It's over to you. So here's the question for you. Give you 2 normal distributions, x and y. And I've told you that the score for x is 13 and a score for y is 18. I want you to compute the z-score for x and do the same for y, and then reach a conclusion. Compared to the overall population, which one has this person done better in actually? So I'll give you some time to do that, and then we'll look at the answers. So pause the video and have a go. answer for the z-score after 3. 1, 2, 3. 1.5 for the z-score for x. For z-score for y, it's 1.2. So compared to the rest of the population, which one has this person done better in? Has he done better in x or y? Well, done better. The x score of 13 has a z-score of 1.5. So, and you can see that the z-score for y is 1.2. It's lower. It means that a smaller proportion of people scored higher than 13 for the x, because, wait, hang on a minute. Yeah, fewer people because there's less area in that tail. Here is more area because it's 1.2, which is less than 1.5. So let's just stop rambling there. So what I'm just saying is that this person has done better the x score than the y. Compared to everybody else, that is. And that's the case even though the y here is bigger than the x. Now it's not always like this. You can have, sometimes it's quite simple. You can find that if one score is bigger than the other one, that person has also done better compared to everybody else in that score, in that exam that he scored higher in than the other one. But I'll give you 2 examples here where that's not the case. Okay, that's it today, folks. I'm Phil from Statistics Mentor.